I will now introduce the concept of a derivative of a multivariable function. We'll start with a simple example. Suppose that a mobile provider charges $40 a month for a data plan, and then $15 for each additional gigabyte over the initial plan of 8 gigabytes. So in other words, the cost of this plan in terms of months M and G gigabytes over the initial plan is equal to 40 times M, that's the $40 a month times the number of months, plus 15G, that's $15 for each additional gigabyte. And now I want to look at the concept of rates of change with this multivariable function. In particular, if I want to take the derivative, do I take the derivative where M is the variable? Is G the variable? Do I take the derivative with both M and G being variables? So let's try to simplify this problem by looking at essentially a single variable function. So let's pretend that the number of months for this mobile plan is going to be 12. And so then we have the single variable function C of 12 times G, which is 40 times 12 plus 15G. Well, then the rate of change of the cost of this data plan would be C prime of G, that's going to be 15. So here, if the number of months for that data plan is fixed at 12, then the cost of the data plan is going to increase by $15 per gigabyte. And that was just kind of the given information. So that derivative makes sense. And we call that the partial derivative of C of mg with respect to the variable g at the point 12g. So when we fix the number of months for this data plan at 12 months, that allows us to take the derivative of a single variable function, and so we're going to call that the partial derivative. Now there's a special notation for the partial derivative. It has this script d, and we're going to take the derivative of the function c, and then we're going to have another script d, and then the variable that we want to take the derivative with respect to in this case is going to be g. So we'll just say dc dg, okay, but this means a partial derivative. That's a derivative where g is the variable, and in this case, we fix the number of months at 12. Well, now let's fix the number of months not at 12, but at some fixed number m. So we're going to pretend that m is a constant. Well, then what is dc dg? Well, if m is a constant, and I'm looking at 40 times m in my function, c of mg, well, the derivative of 40 times m should be 0, because m is constant, and so 40m is constant. And so the derivative here is still 15 when I take the derivative with respect to g. And so we can interpret that the same way. We can say if the number of months is fixed at m, then the cost of the data plan increases by $15 per gigabyte. Okay, but now let's look at it with respect to the other variable. What if we want to find the derivative of c with respect to m at, say, some number? We'll call that number, I'm going to change that real quick. That number is going to be 2. Well, we have to first calculate, well, what is C of M2? C of M2 is going to be 40 times M plus 15 times 2. We can rewrite that as 40M plus 30. So this is a single variable function. So if I want to take the derivative of C with respect to M, well, then I'm just going to take the derivative of this single variable function. This is going to be at M2. And that's going to be just 40. Derivative of 40M is just 40. Now let's interpret what that means. So if the number of gigabytes is fixed at 2, so the number of extra gigabytes that you have that month is fixed at 2, okay? The cost of the data plan well, it increases at a rate, and that rate, of course, is $40 per month. Okay, so that works as a single variable function. What if we want to think about what is dc dm, where we're going to evaluate that at m and g? What is that derivative going to be? Well, hopefully you'll see that C of mg, right? I'll rewrite it for us here. C of mg is 40m plus 15g. And here, we're going to let g be constant. M is going to be our variable. G is just a constant. Well, if g is a constant, then 15g is a constant. That's just a number. And the derivative of 15g will be 0. So the derivative here is still going to be 40. And so we can interpret that as saying if the number of gigabytes is fixed at g, the cost of the data plan it still increases by $40 a month. And that's really the concept of the partial derivative. What we're going to do is we're going to hold one of the variables constant and then take the derivative with respect to the other variable. And that will give us what is the partial derivative. Okay, so let's look at the formal definitions. Okay, so we want to define what is a partial derivative. So the definition is the partial derivatives with respect to x and with respect to y of the function f of xy are the functions that are defined by, well, we have df dx and df dy, and now we want to give a formal definition. Well, let's just remember, what is the derivative of f with respect to x? What is that definition? I believe that definition is the limit as h goes to 0 of f of x plus h minus f of x and then all over h. That was our definition when we had a single variable function. But now f is a function of x and y. So what we're going to do is we're going to leave y constant. That was our whole idea of the partial derivative. So here I'm going to leave y as just y. I'm not going to change y. So that what I'm really doing is I'm looking at this difference quotient where I'm changing x by a little bit. And I'm trying to find the rate of change when I just change x a little bit and I leave y alone. And the limit takes that from being an average rate of change over the interval from x to x plus h, okay, to being an instantaneous rate of change. So what is df dy? Well, it should be very similar. Now, the book likes to use a different letter, k. There's no reason we need to use a different letter, but I will to be consistent. But it's the limit as k goes to 0. Now, x is I'm going to let remain constant. And then I'm going to change y by a little bit. And then I'm going to subtract f of xy. So here I have this difference quotient where I'm looking on the interval from y to y plus k. And then this expression gives me the average rate of change, that difference quotient does. And then the limit from as k goes to 0 gives me the instantaneous rate of change. And so these are the definitions of the partial derivatives of f with respect to x and f with respect to y. Now, of course, those partial derivatives only exist when the limits exist. Now let's make a note. The partial derivative, df dx, describes how f changes when x changes and all other variables are held constant. So in fact, if we have more variables, we can have x, y, z, w, etc. df dx is always going to be changing x and leaving all the other variables constant. So if we want to compute df dx, then what we do is we consider all the other variables to be constants. So that means that all of our derivative rules apply. We just have to know which letter is the variable and which ones are the constants. So let's look at a couple examples. Okay, so we have a function f of xy, which is x squared plus 2xy squared minus y cubed. So df dx in this case, well, x is the variable, so the derivative of x squared is just going to be 2x. And then, what is the derivative of 2xy squared? Well, x is the only variable. What's left is just 2y squared. So in fact, it might be easier to think of this as being 2y squared x. And then 2y squared is just a number sitting in front of x. And what is the derivative of a number sitting in front of x? Well, it's just the number, right? The derivative of 4x is 4. The derivative of 10x is 10. So the derivative of 2y squared x should just be 2y squared. And then, what about the derivative of y cubed? You might be tempted to say it was 3y squared, but y cubed in this case is going to be a constant. X is the variable. So what's the derivative of something like 2 cubed? Well, that's the derivative of 8. It's 0. What's the derivative of 5 cubed? Well, that's the derivative of 125. So that's 0. So the derivative of y cubed in this case is just 0. Okay, now let's move on to the derivative of f with respect to y. Well, the derivative of f with respect to y, well, that's going to be, well, the derivative of x squared with respect to y. So x is a constant, so that's a constant squared. So that's just another constant, and the derivative of that constant is 0. So the derivative of the first term is just 0. Now, what about 2xy squared? Well, here, 2x is a constant. And now I need to take the derivative of y squared, which is 2y. And so if I had the derivative of, say, 8y squared, we would say it was 16y. If I had the derivative of 12y squared, we would say it was 24y. So the derivative of 2x y squared is going to be 4xy. Okay, so we're going to bring the 2 down like we did before, multiply it by the constant that's in front, which is, in this case, 2x. So 2 times 2x is 4x, and so the derivative there is 4xy. And then, now what's the derivative of y cubed? This time it is 3y squared because y is our variable. Okay, let's do something just a little bit more complicated. let's take the derivative of f of xy, which is y e to the x squared times y. X is going to be our variable first. That means that y is constant. So the derivative here is going to be y, because that's just a constant. And then e to the x squared y, well, the derivative of e to anything, right, is going to be e to that thing times the derivative of what's inside the box. So what is the derivative of x squared y? Well, y is just a constant, so that derivative is going to be 2xy. So we can simplify this if we choose. It's going to be 2xy squared e to the x squared y. That's sometimes helpful when working with the expression, but it's not necessary to simplify to basically say what the derivative is. Okay, now let's take the derivative with respect to y. That's going to be a little bit more difficult, because now I have a function of y that's a product of two functions of y. So I have this function, which is just y, and then I have e to the x squared y. So I need to use the product rule. So I'm going to kind of write a reminder of what the product rule is. I take the derivative of that first thing, I leave the second one alone, plus I leave the first one alone, and then I take the derivative of the second thing. That's a little shorthand for the product rule there. So in this case, the derivative of y is 1. I'm going to leave what's in the triangle alone. That's e to the x squared y. And then I have y, which I'm going to leave alone. That's that box. And then the derivative of the triangle, that's the derivative of e to the x squared y. The derivative there is itself, e to the x squared y, times the derivative of what's in the exponent. What's in the exponent there is x squared y. So the derivative of x squared y with respect to y is just x squared. So here, when I use the product rule, I also still have to use the chain rule, and that's what's sitting inside the exponent is x squared y. And the derivative of x squared y in this case is just x squared. Okay, so I can simplify this in some way if I like. There's lots of ways to simplify this. I could write this as 1 plus x squared y times e to the x squared y if I want to factor that out. And so that's the partial derivative of f with respect to y. One last thing that I want to bring up is that there's actually several notations for partial derivatives. Just like we had df dx or f prime of x, right? We can have an alternate notation for partial f, partial x. And that notation that we use is f sub x. We can't use a prime here because if we did f prime, we wouldn't know what variable we were taking the derivative with respect to. So we use a sub x. So f sub x, if you see that notation, means the partial derivative of f with respect to x. And then f sub y means the partial derivative of f with respect to y.